There's a frame arrestor over there. So this kind of heating method is, we don't heat gas directly. We heat water, and water heat gas. Correct? This green thing is water, so we heat water first, and then water heat gas. This kind of heating is indirect. Very clear, right? We heat water first, so it's indirect method of heating. Alright? So, zoom in version. Look at this one. We have gas go in, heating, and go into several coils. And then go out to the choke. So we choke later. And another side, it may go back and heat again, go several parts, and then come out. Okay? So heat first, then go through choke. Just that. If you say choke first, that's -1, okay? Pressure drop from choke cause temperature to drop. After the drop, temperature should stay above the hydrate formation line. Some type of line heater let the hydrate form a little bit and melt the hydrate. I'll show that. Okay, here. Split pass coil. Split pass coils or choke is in between. So this one choke is over here. So you see P in, T in over there? That is T in, P in. We heat it. And then choke is in the middle. We choke it. And then we heat it again and go out. Okay? So this is another type. Split pass coil. Okay?
What's the advantage of that?
What's the advantage of this one? I think after we do the calculation, you will see which one is cheaper and then buy that one. Okay. At the end, I think I don't know for sure what's the advantage. The example from the textbook say like, okay, do one calculation and another calculation and select the cheapest one. Do you have anything to add? Is that better?
Sometimes you'll take a pressure drop. You got especially got an especially high pressure well. You won't want to take all that pressure drop through one choke because of erosional velocities. And so you'll take enough of a pressure drop where you can go through that expensive heavy wall pipe at high pressure. Then you can take a drop. Now you're working at a lower pressure. You put a cheaper second pass of coils in there, and that second pass is heating it up. Take further pressure drops that you're going to have in your process system as you go through.
So we can choke.
Not at one time.
Multiple chokes?
I'm sorry?
Good for multiple chokes? Multiple chokes?
Chokes, yes.
Yes.
Using, you may have a choke at the wellhead even prior to heating to drop some of the pressure. Any place you drop that pressure, you're going to reduce pipe size or pipe pressure rating that you're going to have. So you can drop that pressure rating some at the wellhead without the hydrate formation. Take it through a coil, heat it, and take either your final choke or a second pass if you're going to anticipate additional pressure drops through your system somewhere later.
Do you have to account for extreme weather when you're heating up fluids or pipe?
Do you want to account for that? We can,
Select the best.
but I skip all that calculation because they complain it's too difficult. We can account for that for sure if you want to. To account for that, we have to do heat transfer calculation. Like if let's say wellhead is 100 feet away or 200 feet away, what should be the temperature once it reaches this point? Okay, there's some kind of calculation to show, okay, the temperature will drop below hydrate temperature or something or not. Most of the time, you just bury the line and it just works. Okay. Just bury the line and it just works. Or insulate. They insulate. I think they just bury the line. In the subsea pipeline, you have to insulate it because it's so long. In the subsea pipeline, that's where you will actually do the calculation because it's not just hydrate. So when the temperature drops below a certain temperature, wax can form. Question?
So right off the wellhead, do you usually have like multiple chokes before you get to this? Because you're actually running it through here and heating it, and then you're running it through a choke, so the pressure's gonna, the temperature's gonna drop, so you heat it, drops, and you're heating it back again. So like, do some of these just not have chokes, and you choke it off before it actually runs through the line here?
What's your question? The question is, do we
Like, because
choke it several times?
you're heating it, right? And then it's going through a choke right there, and so the temperature's gonna drop, right?
Temperature drop and we
So
heat
then
it
you're just
again.
like, yeah, so I'm just curious if you choke it all before it actually goes through, where you don't have a choke inside the line here. It's like basically reheating it.
Where should we choke it?
Yeah.
Should we choke it right at the wellhead? So the one of the reasons that we choke it is because the temperature is too, the pressure is too high, and we want to meet the pipeline pressure or something, right? The pressure is so high. So we can heat it at the wellhead too. I have seen it right that way in the textbook, but in addition to that, we have to place the line heater somewhere that it take gas from multiple well or something. So if we have 10 well and we decide to choke right at the wellhead, so we have 10 choke. Of course we can close the well, but if we have just one unit and heat the gas altogether, that may be better. Want to add anything on this?
You like to take that pressure drop down, you're reducing cost, you get a cheaper pipe. But every time you take a pressure drop, yes, you will be adding some energy back to reheat it. But when you reheat it, you're in cheaper pipe.
So whenever we choke it, make sure that there's no hydrate by this line heater. So this one and beyond is just a calculation that sadly you have to do it, okay? And it is in the, it will be in the homework. I don't think it's in this homework yet. I emphasize again, this type of heating is indirect heating, okay? Typically, high pressure coil and low pressure coil we can have. So one side before choke is high pressure coil. Oh, that's the reason. So another side is low pressure coil. So low pressure coil will be cheaper, right? Cheaper than high pressure coil. And it limits the bath temperature to be 190 to 200 F to avoid evaporation. So we can use glycol. Glycol can be added for higher temperature. Okay. But for water, it's just 190 to 200. So use just water may be a little bit better in the heat transfer point of view. Because water has lower viscosity, okay, than the mixture of water and glycol. If you have 50% glycol, 50% water, viscosity go up. It's become thicker, okay. So it doesn't move that fast and it's kind of reduce the heating a little bit. But if you want to heat it more, add glycol. But use just that, maybe cheaper. Water should be cheaper than glycol too, right? Okay. So preheat coil must have rating of shut-in pressure of well. Okay. That part has to be shut-in pressure of well. So it has to be strong enough. The wall has to be thick enough. P in, T in, P out, T out are outside the hydrate phase envelope. Okay. Before it go inside and after it go outside, we should not have hydrate. TB is the temperature of the bath, water temperature. L1 is the line length of preheat section. So this part is L1. Okay, that is the length. Okay. In the calculation, they assume P at T1. See that T1 equal to P in. So there is no pressure loss, and it's go to the choke. Okay. Temperature at point 2 is below hydrate temperature. See that? After the choke is below hydrate temperature. So that is why we have coil L2 to melt the hydrate that are forming. Okay. This is an approach that they use to do the calculation. Just assume no pressure drop. And then go back, use that chart. So we know shut in pressure, right? Then we can start at one point. So inlet pressure is assumed to be the same as this pressure. Pressure at that point assumed to be the same as the pressure at that point. And then do calculation. Good. Okay. L1 pipe diameter is smaller than L2 pipe diameter due to gas velocity. What is this about? Why, Eric, what is that? Victor, why should we do anything like that? L1 pipe diameter is smaller than L2 pipe diameter due to gas velocity. So Victor, when velocity go up, does it make noise? Yeah, it may make noise, right? If we have a little bit of sand at higher velocity, we will erode the pipe more. Go get her name. What's her name? Give her the sheet. Says there. Are you in this class? Probably not. No, okay, it's okay. So for the velocity, if we have a little bit of solid particle, Victor, what do you think happened? So that particle, should it hit with the pipe wall? Right? It should hit with the pipe wall. So who else want to get A plus? Who want to get A plus? Savib, is that your name?
Yes.
Okay. What do you think when we have solid particle?
Small size.
Small size of solid particle at a high velocity. Erosion, right? So we have to keep the velocity lower than a certain velocity. So if that solid particle moves slow, it doesn't erode the pipe that much. But if it hits fast, it eats the pipe quick, right? So L1 pipe is smaller than L2 pipe due to velocity. So do you know why that is? Is it clear? Not yet. Okay, let me tell you this. After the choke, gas expands, correct? We have pressure drop. When pressure drop, gas expands. This means that if we have the same pipe diameter, it expands, it will move faster. Okay, it moves at a constant mass flow rate, right? Mass flow rate go through the system is constant. When it expands, it moves even faster. So if we don't make the pipe to be bigger as it expands, velocity could be high enough to make erosion problem. Okay? But also the pressure also go down. We may use a thinner pipe, which is cheaper, less pressure rating. Good? So we have to calculate the erosional velocity to be able to answer that question quantitatively. Okay? So I refer to API 14E for erosion corrosion problem, and we will talk about that at the end. Chimney should be long enough to let lower density exhaust go out and keep higher density air inside, minimize the loss of air in the tube. Okay, that's minor point. So that's for chimney. Heating can be number one, before and after the choke. So this is split pass coil. Okay, or only after the choke, single pass coil. Okay. Only after the choke. I think I know why students cannot do it right last year. Maybe because of me. Good. Only before the choke. In the Silver's textbook, it's discussed something about only after the choke too, but they said don't do that because it may plug or something. It's not good to choke it first and make it plug and then melt it because it may. You see the choke. There's some part over here that you may not have enough time to melt it, so and it's not good. So heating can be only before the choke, not after the choke. I correct it and you correct it too, okay? Steel can get brittle at low temperature, minus 40 to 0 Celsius, but we should not go that low anyway, right? Because we will form hydrate. Okay, look like this. So that is the choke. That is choke. Okay. So this one, that's one is the choke. And we have the coil inside. And see more at the field trip. Now we want to know the size. How big should it be? Okay. At the end, we want to buy the right line heater. We don't want to buy the line heater that is too big. Let's take a look. What do we need when we buy the line heater? You see this maximum coil working pressure. So we want to know how big is the pipe or coil that is inside. Is it 1XS? Standard, I think is schedule 40. XS is schedule 80. XX is schedule 160. Okay, and we will have to tell this one. So when you call Silvers, you said you want to buy line heater. They want some information from you because there are so many of them. Do you want to buy 24 inch by 3 feet? Is that the size that you want? Or you want a bigger one, or very big one like this? 24 feet. Oh, 24 feet is quite a lot, and 72 inches. Do we want to buy that one? Very big one. Or you can go with a small one. We don't know. We need to know how much is the firebox rating that we need in BTU per hour. Do we need 100,000? Is that enough? Or we need 500,000? We need 1 million. They want you to buy a bigger one, of course, because they make more money that way. Okay? Very clear, right? And so let's say we know firebox rating, so 1 million BTU per hour. They will ask you, do you want 2 inch or 3 inch? Or when they decide to you, oh, should I do 2 inch or should I do 3 inch? So if I have a bigger pipe, so there are several options, right? 2 inch, 3 inch, 4 inch. They will want you to buy biggest pipe possible because that's more expensive, okay? Want you to use XXX rating or XX rating. You see, X and XX schedule 80 and 160. 160 XS is thicker wall, is more expensive. We don't want to buy it, but if we need it, we want to buy it. How do you know that you need it or not? You come to class next time, maybe. Next time, I have just 4 minutes left, so next time we will cover this. Heat duty equation. Oh, okay, for this amount of time that we have left, let's go through this slide completely. Okay. We need to know heat duty. I just show you how many BTU per hour. Okay. We need to know size of the fire tube, coil diameter, and wall thickness. Okay. X or XX or standard. We need to know coil length. They provide several lengths of coil. Okay. That's the way to do the calculation for coil length. And 10,000 BTU per hour per cubic feet is used to estimate coil length. So, Ashley, what is this? BTU per hour per square feet.
I'm not sure.
Is that heat flux? Amount of heat? Heat duty? What do you call this in English?
I don't know.
Or you want me to call it Thai or something? That is heat flux. Okay, heat per time per area. That is amount of heat per unit time per unit area. Ashley, what is that in SI? Chris, what is that in SI?
Watt over foot square.
Oh, yes, I see meter. Watt per meter square. Very good. So the unit will be in the exam. Okay. Last thing to ask you. Okay. Last thing to ask you. During the calculation, we will have. You will need to know some kind of specific heat capacity. Okay. Specific heat capacity of water. What is the unit for specific heat? CP. Chris?
Say that again, I'm sorry.
CP. C sub P. Specific heat capacity. Have you ever heard MCP delta T equal to heat requirement or something?
Yeah, that sounds.
Okay.
For the-
So specific heat capacity is the amount of heat that required to raise the temperature of water up for 1 degree, for 1 kilogram. The unit is Joule per kilogram per Kelvin. That is the unit. In field unit will be BTU per pound per Fahrenheit. Okay. BTU per pound per Fahrenheit. That is in field unit. So before you go, I want to ask you this question, and we will talk about it more next time. How do I change from BTU per pound per Fahrenheit into BTU per pound per Röntgen? So I have find out who want to volunteer to do something? Victor. Okay. Tell me next time what is the specific heat capacity of water? Of water in the unit of BTU per pound per Röntgen. And Victor, you will tell me how to change that to how to do the unit conversion to BTU per pound per Fahrenheit. How to change from Röntgen to Fahrenheit. Oh, it doesn't change? Okay. We'll talk more next time. So you tell me the number, okay, how much is the specific capacity of water in that unit. Do the homework. The homework due 11:59:00 next February 2nd, next Thursday. Okay. You have to write 300 words about academic integrity or something. So you have to type something. Don't copy from your friend. Okay, goodbye. Can you stop the camera?